Today we talk about the lecture 7, stochastic computation graphs and pathwise derivative policy gradient methods. We will talk about two things in this presentation. First, framework how to compute gradient of expectations in general. Second, different class of policy gradient methods than the ones we've been hearing about so far, where first one, changing probability of your actions like WQ running, and second one is instead of writing loss function, probability of action times advantage, which is expectation of reward, value function that tells you how you should adjust your actions, in which direction you should adjusting the action. Contents are following. First one is stochastic computation graphs SGG algorithm. Second one is pathwise derivative policy gradient methods. And third and fourth one is not covered in the presentation, and fifth one is updated by the next time. So let's begin with the motivation of stochastic computation graphs SGG. The gradient estimation is at the core of much of modern machine learning. In the sense of the getting gradient estimation, backpropagation is the good way to get gradient estimation. Backpropagation is mechanical. This gives us more freedom to thinker with architectures and loss functions. And in RL, we cannot apply backpropagation in general. There are two reasons. First, the loss function is not directly differentiable. It may be possible when we use another way, but it might have some non-differentiable components. So in next slide we'll show details. Second one is about components in loss. We cannot access to component perfectly because of expectation form and number of states and number of actions and unknown probability. In RL, agent is known as well as the agent is known, so we knew functional form of the agent. In this argument, agent is neural network and loss function, but we cannot access to environment, so it can be the information of environment is derived from interaction between environment and agents. So when we estimate gradients, we cannot calculate it analytically with writing down on paper. There are two ways to get estimation of gradients. First one is already mentioned. Calculate full functional form of loss function. Apply backpropagation algorithm called backprop style. And next one is get gradient using policy gradient method called reinforced style. In RL, we use reinforced style estimator like this form. sometimes we need some combination of both estimation when we use recurrent neural network and policy. Policy is from the neural network, and the H is hidden state in RNN. In every time step, we cannot see the full states of the full hidden state, so we need another way to calculate estimator. Also, there is an updating equation which is differentiable in RNN. We will do backpropagation through time. Also, we will use reinforced style estimator to know how the action probability can affect the reward. Also, we sometimes use non-differentiable function instead of reward function. When we learn the classifier, we make hard attention model. It is shown the next slide. So its objective is log of the probability of correct label. Also, in this case, reward has some structure which we cannot look inside. There are many model papers which apply one or two estimation technique. Each paper has their own convoluted derivation of gradient estimator, but we will see general framework first. Let's look at gradient of expectation more formally. F can be the loss or reward. We determine the theta that will optimize. The important problem is what estimator we will use. To know it, we will catch where the theta is. If theta is in the distribution, like parameterized distribution, gradient estimators are following this form. It is a reinforcement estimator in policy gradients, and X is trajectory. It is called score function estimator. Next one is that the case that theta is in F when distribution is fixed form. In this case, we can switch expectation and gradient with some mathematical conditions like continuity or differentiability. It is shown in most places in machine learning. Also, when we do the random dropout in neural net, this kind of shapes are shown. Dropout cannot be parameterized, just is picked from the fixed distribution. In this formula, it is from the normal, but dropout case, that is from the Bernoulli 0.5. In dropout mask, gradient of expectation is the same as the expectation of gradient in the dropout case, so it is called pathwise derivative estimator. It doesn't expand on the object or problems, we can get two forms and cases because we change one to another by parameterization. But in this case, we cannot say that both forms are differentiable. Next one is stochastic computation graphs. Form of stochastic computation graphs. It is DAG, directed cycle graph. DAG means a finite directed graph with no direct cycle, like this one, this form. In this form, there's no directed cycle. Also, directed graph is a graph that is a set of vertices connected by edges. Edges and vertices are connected, and edges has some directions, not the cyclic way. Stochastic computation graphs is a way to describing some computation of the gradients estimation. In SCG, each node corresponds to a deterministic or stochastic operation. What we are going to do here is to show how to automatically derive unbiased gradients. When we have any loss function which described in this graph, the graph will give you unbiased gradient estimator according to the loss. Left one is normal computation graph. In each node of computation graph, we can imitate value. We can intermediate value. We can get some immediate value. So we use loss function in the end, and loss has some parameters. Those parameters can exist in each nodes. We revise it with some backpropagation. Its examples are fully connected neural network or convoluted neural network, and so on. But stochastic computation graphs has some stochastic nodes, like this one. This node means that stochastic process exists in this direction. It isn't deterministic function of parents. Parents of the stochastic node is this. Neural network with some dropout is one of the stochastic computation graphs, and will shown later. One example is hard attention. This is simplified model of hard attention with some main points. It is non-trivial to calculate the gradients of loss function that we want. First, to look at the input image. Observation 1 is called O1, and then we determine some kind of crop window A. Our action is choosing a crop window and get cropped image from the input image and crop window, and output is the guess of the label for the input image. So we construct neural network in two ways. It gets label of cropped image. We give it a reward for getting the right label. There are two ways to define the loss. The first one is output is label, like this one. If it is correct, reward is 1 and 0 otherwise. We want to learn parameters. So those parameters not only determine your choice of window and A is using the second observation. To get second observation, we use this window, and also when we get some label, we have some parameters to get labels, and after get label, we find reward of it with some true label. So when we get in this process, when we get some wrong label, we cannot use correct label information. We just use the on-off kind information. So we throw out some true image information. For example, there are like 10 labels. First model says wrong label. In various input image, we only get the information about the correct label when you happen to guess the right one. If you have some wrong label in the many case, so it is because this is the first model, we cannot get the beyond the on-off information. So instead of defining this loss, we consider other loss like this form. The loss specifying some probability like 0.2 for cat and 0.5 for dog. It is probability distribution over label k, kappa in this case. Probability of or log probability of correct label is reward. Details of the gradient estimator in this case is talked later, but we get some intuitive. We need estimator for action and label in this case also. Gradient estimator of this model might be the gradient probability of action times reward plus gradient of log probability of the label times reward. We can find direct back propagation with some path. Next one is the abstract example, designed to illustrate all the different kinds of motifs we have to deal with, or that we want to our general framework to dealing with. Diamonds is loss is deterministic operation, and diamond means it is a loss function. In this case, loss is C plus E. In this case, stochastic node B shows that when A and D are given, there is some distribution that estimates B, and we have two parameter theta and phi. It determine the loss. So we want to get gradient of loss, which is gradient of expectation of loss according to theta and phi. If it is deterministic, we just use backpropagation, but it isn't in this case. So we construct surrogate loss, this form. Let the stochastic node be a constant in one calculation. We have new form of loss that is log probability times future cost minus optimal baseline with some stochastic node. Optional baseline comes from the policy gradients. It reduces the variance while it doesn't affect to the mean of the gradient estimator of in this model. So surrogate loss we can obtain some unbiased gradient estimator by differentiating surrogate loss. This form is C plus C original loss plus the second term is the like this one, log P probability of the probability of the stochastic node, and hat means in this process, in one process it is regarded as some constant. First term in this loss shows the effect of deterministic change to the cost to the loss. Second one represents how the parameter affects to loss with changing probability. In summary, there's a parameter which directs affect to the loss and another parameter which affect the distribution. Results are followings. General method for calculating gradient estimator is followings. Surrogate loss version, which explained in previous page. Each stochastic node gives a loss expression log probability of node value times sum of downstream cost. It is from the fact how the parameter affect distributions. The sum of costs are treated as variables. This one, sum of costs is treated as variables. So alternative generalized backpropagation is one of the general method. Add some new operation. When doing backpropagation, if we start in stochastic node, we apply the follow spatial calculation. Unlikely the normal backpropagation with Jacobian backpropagation, we use gradients of log probability times future cost of the backpropagation. Future in this case, future cost is the downstream is the same with the downstream cost. So next one will present it by Minjung-Chu.
I will explain about deriving the policy gradient reparameterized. Let's talk about episode MDP. In here, theta is policy parameters. S1, S2, these are states. States are all stochastic with stochastic transition. And A1, A2, these are actions. Actions are depending on parameter theta and current states. Next states are depending on current actions. These are stochastic computational graph, looks like for policy gradient methods. Let's say, for simplicity, that the reward exists only at the end, and it is deterministic of the state. Then, our reinforced gradient estimator looks like this. There are numerous continuous problems, such as robotic control problems from a Gaussian distribution. Therefore, we can reparameterize this graph as using z with mean 0 and standard deviation 1. Then, actions will be deterministic function, and graph looks like as follows. The action equals pi of s, z, theta, where z is some random noise with Gaussian distribution. But in this graph, some problem occurs. For the case of p as 2 bar s1 a1, we cannot represent this clearly since a1 depends on the theta. Therefore, when we calculate gradient estimator, we have to consider the a1 as the function of s1, random noise z, and theta. Then, gradient estimator formula should be switched like this. In reinforcement learning, we don't assume that we know the model of the system, so we do not need to access transition model P. But according to this this formula, we have to access the P. That means it only works if P S2 bar S1A1 is known. Therefore, if we do not have the dynamics model, we can't use this form to actually compute a policy gradient. Let's imagine what happens when you wiggle the parameters. How is that going to affect the loss? When we've passed the deterministic nodes, we can flowing outwards, and otherwise, for the deterministic nodes, it gets lost. In this case, if we wiggle the parameters, it propagates through the action, and then it goes to the probability of the next state. But we don't know the function of S2, the problem occurs. Let's consider the gradient estimator in this case in details. Formula can be rewritten as follows. Reward R is depending on theta. R's theta should be contained in here. And we add log P S1R plus log P S2 bar S1A1 R. Let's differentiate this with respect to theta. For differentiating R theta, all the stochastic nodes can be considered as constants. So we can ignore this term. Second term doesn't have any dependence on theta 2 because we're treating both S1 and reward as constant. So we can ignore this term too. In here, action does depend on theta. We can expand it into Jacobians, but it is terribly useful. So we need to know this function to be able to compute that term unless we have access to this function. Thank you for my presentation.